are these Weil semimetals where we have individual kind of Weil points that are not doubled, and this kind of Dirac semimetals, which you can picture, as Sid mentioned, as doubled Weil semimetals of opposite chirality, but protected from mixing by some crystal symmetry. And as a theorist, the reason we're interested in these materials is that they give you a new example of new kinds of topology that can arise actually without a band gap. So normally we think of topological effects as arising from some protection by a gap, but actually if you have a band touching, you can get new topological features, say singularities and Berry fluxes, that can only arise in a gapless system. And the Weil node is a particularly good example of this. Because it serves as a monopole source of churn flux. And there are two main consequences that have grabbed people's attention, which we've heard a lot about in the previous talk, so I'll just mention them briefly. The first is that if you apply electric and magnetic fields, you end up with this charge pumping between upstream and around Weil nodes, and this is mediated by a very special Landau level, which is near the Weil node. The lowest Landau level is independent of magnetic field. Its energies are independent of magnetic field, and it disperses exactly along or against the magnetic field. And this serves as the channel which mediates this chiral pumping between valleys. And another manifestation of this topology, so like any good topological material, while semimetals have surface states, and as Sid nicely explained, if you take a surface that the two Weil nodes don't project onto the same point in the surface Brillouin zone, there's some kind of imprint of the Dirac string connecting these two Weil nodes, which is a line of chiral nodes that forms kind of half of a Fermi surface. And this is again something that can only happen in a gapless system, because in order to have, in a gap system, any surface state, there's a nice dividing line between occupied and unoccupied states in the surface Brillouin zone. And so in that case, the Fermi surface of the surface state has to be a closed surface and not an open arc. And so this open arc really relies on some direct tight connection to these bulk gap closings. And so the key players in this whole story about the topology of Weil semimetals are this chiral bulk Landau level and the surface Fermi arcs. And today I want to talk about an experimental probe which can reveal both of these features in a precise way, which is to look at quantum oscillations associated with this Fermi arc surface state after applying a magnetic field. And the goal will be to come up with a way to measure these Fermi arcs surface states and to reveal their topology in a more precise way than is available in ARPES, which gives you a nice picture of these surface states. But it's hard to look at, what's happening here. Are they really forming a closed surface state? Are they meeting some bulk Fermi pocket? Or are they just some kind of conventional surface orbits? So I want to start with outlining some theory about what happens when you turn on a magnetic field in a Weil semimetal. In the second half of the talk, I'll discuss a little bit of some experimental measurements by James Van Leitz's group and MIT. So the theory part was done in collaboration with Itamar, who I believe is in the audience, and he will be a postdoc at MIT starting very soon, and also Ashwin. So just as a reminder, I'm sure everyone in the audience is familiar with this, but quantum oscillations by applying a magnetic field is sort of a classic way of getting a precision measurement of a Fermi surface. And the main idea is that when you apply a magnetic field, semi-classically electrons just orbit equipotential lines of your Fermi surface. And if you look at quantized versions of these magnetic orbits, they pass through the Fermi level in a periodic pattern and when plotted against 1 over the magnetic field. And the period of these oscillations tells you about the extremal orbits of your Fermi surface. And by changing the angle, you can get very high precision data about the shape and structure of your Fermi surface. And these blips show up in anything that's sensitive to density of states, so magnetization, I'll be talking mostly today about conductivity, but also they show up in tunneling density states and most physical probes. So if we want to apply this kind of measurement to a wild semi-metal, we immediately face a conundrum, which is that if I start an electron in the surface Fermi arc, and I turn on a magnetic field, the electron will slide via the Lorentz force towards the end of the arc. But at the end of the arc, where does the electron go? So as we slide towards the end of the arc, we notice that actually the bulk band gas is coming crashing down. And so this single band picture that we usually think of with semi-classical orbits is breaking down. And you can show that what happens is actually the electron gets shoved into the bulk state, the only place for it to go. So once in the bulk, what happens? So it's easiest to think at very low energies, the only state available is actually this chiral Landau level for the bulk. And this chiral Landau level can act as a kind of one-way moving conveyor belt that drags the electron to the opposite surface, the bottom surface of the sample. And there it finds kind of its missing partner, the rest of this Fermi surface that I've kind of divided across the sample. And then so on the bottom surface, kind of complete the other half of the orbit in exactly the same manner and get a closed magnetic orbit. And so this will be the source of all the phenomena that I'll talk about. And so I just want to make a couple comments. This is an interesting orbit. It's a closed magnetic orbit on a non-local Fermi surface. And it's some mixture of some semi-classical motion and some quantized chiral Landau level motion. And one bizarre feature of this is that it actually can enclose zero flux relative to the magnetic field. So the real space motion of this can actually be completely parallel to the magnetic field, which is something that won't happen for conventional cyclotron orbits. And the other thing I want to mention is that even though I kind of motivated this orbit at low energies where the bulk chiral Landau level is the only state around, you can easily convince yourself that this orbit occurs at any energy where there's this bulk chiral Landau level. And the reason for this is that if I look at this bulk chiral Landau level, I can't form a closed quantum orbit with just one chirality Landau level. I need both. And the only way they can connect at small fields, because momentum you can think is not quite conserved, but it's roughly conserved up to the inverse magnetic length. And so if the inverse magnetic length is much less than this arc length, the only way they can connect is by sliding along this Fermi arc. So there's a really topological connection that when I turn on the field, I reveal that this Fermi arc is actually the same state as this chiral Landau level. They're intertwined. So I can get to some actual quantum levels from the semi-classical orbit by using the Bohr-Sommerfeld quantization condition, basically demanding that the phase I accumulate around an orbit is an integer multiple of 2 pi. And the phase is just the energy of the orbit times the time, semi-classical time it takes to circumnavigate the orbit. And here the time has two components. One is how long it takes to slide along the arc, which is the arc distance divided by Lorentz force. And the other is how long it takes for me to kind of propagate on this chiral Landau level